Okay, we're going to start the second chapter on forces, chapter 6, which is going to be mostly focusing on friction. Okay, so frictional forces are very common in our everyday lives, and in fact they're pretty much everywhere. So to give a couple examples, if you send a book sliding down a horizontal surface, the book will finally slow down and come to a stop. So we have a horizontal surface and you have a book here, you push it in this direction, there's going to be some frictional force acting in this direction. And we're going to say frictional force is given by either that, or most of the time we're just going to say frictional force is given by a little f. Now there's two kinds of frictional forces. There's static and kinetic. So if the book is moving and slowing down, coming to a stop, that's going to be a kinetic frictional force, and that's going to be given by this little subscript k. Now the second situation, if you move a heavy crate, if you push a heavy crate and the crate does not move, then the applied force must be counteracted by the frictional forces. So if we had just a crate here and you were pushing on it in this direction, there's a frictional force acting in the opposite direction, and this is going to be little f subscript s. So that's going to be the static frictional force. So if it doesn't move, it's going to be static. If it moves, it's going to be kinetic. Okay. Alright, so let's look at some free body diagrams of some applied forces. Alright, so if there's no attempt at sliding, thus no friction and no motion, there's going to be no friction. So if you're not pushing on the object, as in figure A, there's going to be no friction. Now, the force F attempts sliding but is balanced by the frictional force. There's no motion, so that's going to be static friction. All right, so you see there's a applied force here. You have frictional force acting in the opposite direction of the applied force. It's not moving, which means it's going to be static friction. Now the next couple examples, C and D, basically show the same thing. You can increase this applied force, and it's going to still be no motion, so it's just a larger frictional force. And then if the applied force is even greater, the frictional force is going to balance it out every time. All right, so depending on how strong the frictional force can be, it's going to determine how high the static friction force can be. So, for instance, once you get the object moving, so finally the applied force has overwhelmed the static frictional force, the block slides and accelerates. So it's going to accelerate, and you have this applied force here. You're going to get this kinetic friction going in the opposite direction. Now this kinetic friction is going to be significantly less than the applied friction, even though it just barely overcame it. Because if you look at this chart down here in figure G, notice as we increase force, the static friction force comes up to this peak. So to get something moving, you actually need to have a lot larger force than to actually keep it constant. So let me say that again. The static friction is going to require a lot more force to get it moving. Once it's moving, you need a lot less force to keep it moving at the same speed. So notice, to maintain the speed, a weaker force or weaker applied force to match the weak frictional force is going to get you weak kinetic motion again, or kinetic friction. Okay. So again, the variables we're going to use is little f subscript s and little f subscript k for kinetic and static. Now, static frictional force acts when there is no relative motion between the body and the contact force. Again, so if there's no motion between the two things that are touching, you're going to have static friction. Now, the magnitude of the static frictional force increases as the applied force to the body is increased, because in order for the object not to move, you need balanced forces. All right, so the static frictional force is going to increase as the applied force increases. And finally, when there's a relative motion between the body and the contact surface, kinetic friction starts to act. Now, usually the magnitude of the kinetic frictional force, which acts when there is motion, is less than the maximum magnitude of the static frictional force, which acts when there is no motion. All right, so that's just a summary of basically what we just said in the last slide. Now, often there's the sliding motion of one surface over another is jerky because the two surfaces alternately stick together and then slip. So some examples of this are tires skidding on pavement, a fingernail scratching on the chalkboard, a rusty hinge is forced open, a bow is drawn on a violin. Okay, so those are things that are sticking and then sticking and then slipping, sticking and then slipping. Some properties of friction. Now, if the body does not move, then the static frictional force and the component of the applied force is parallel to the surface. They balance each other. All right, so they are equal in magnitude, and the static frictional force F is directed opposite the component of the applied force, which is big F. Property 2. Now, the magnitude has a maximum value that is given by this. So the maximum possible static frictional force is going to be given by mu s times the normal force. So F subscript big N is going to be our normal force. This, again, is the normal force, which is sometimes just written as big N. All right. Where mu s, again, is the coefficient of static friction, and Fn is the magnitude of the normal force on the body of the surface. So what is a coefficient of friction? Well, a coefficient of friction is just basically saying how sticky something is. So if you have a large coefficient of friction between two surfaces, then there's going to be a lot of friction. If you have a low coefficient, there's not a lot of friction. All right. So if the magnitude of the component of your applied force that is parallel to the surface exceeds the maximum static friction force, then the body begins to slide along the surface. All right. Property 3. If the body begins to slide along the surface, the magnitude of the frictional force rapidly decreases to a value of Fk given by same equation, but now we have the kinetic frictional force and is equal to mu k, which is the coefficient of kinetic friction, times the normal force. Okay, so during the sliding, a kinetic frictional force Fk opposes the motion. All right, so when something is sliding, this frictional force is always going to oppose the motion. That's the most important part. All right, so let's do an example. If a car's wheels are locked, which means they're kept from rolling, during emergency braking, the car slides along the road. Ripped off bits of tire and small melted sections of road form the skid marks that reveal the cold welding occurred during the slide. The record for the longest skid marks on a public road was reportedly set in 1960 by a Jaguar on the M1 highway in England. The marks were 290 meters long. Assuming that the coefficient of kinetic friction is 0.6, so the coefficient of kinetic friction is 0.6, and the car's acceleration was constant during the braking, so you have a constant acceleration. How fast was the car going when the wheels became locked? All right, so we have a Freebody diagram here. It shows that you have a frictional force that's opposing the sliding. So you have this frictional force going in that direction. Now there's no force going to the right because there's no applied force. The car is not accelerating or pushing on the accelerator. There's nothing pushing it forward. It does have momentum and it's going to have some velocity, but there's no force acting on it to the right. So we don't draw anything to the right. Now, going up, we have our normal force, and going down, we have the force of gravity, as we would draw for everything, every Freebody diagram. All right, so assume that the constant acceleration, A, was due only to a kinetic frictional force on the car from the road directed opposite the direction's motion. All right, so again, if the car is moving in this direction, frictional force is going to be in that direction, always going to be opposite the motion. So this is going to result in this, which is, so if we take our equation for force, which is the summation of forces is equal to ma, and you add all the forces in the x direction only, so we can say this is x, and we can say this is in the x direction, the only force that we have acting is the frictional force. So this is just minus F is equal to max, which is what they have here. All right, where m is going to be the car's mass. Now the minus sign is going to indicate the direction of the kinetic frictional force, right? So we generally will say to the left is negative, so since the frictional force is going to the left, we'll call that negative. Okay, so the frictional force has a magnitude, Fk is equal to mu Fn, which is our equation for our frictional force, where Fn is the magnitude of the normal force on the car from the road. Okay, now because the car is not accelerating vertically, we can say that, well, if we do the summation of forces in the y direction is equal to ma y, add all of our forces together on the left side, so we have our normal force minus mg. So if you look here, we have the normal force going up, so I call that positive, and we have mg going down, which is the force of gravity. All right, now that's going to be equal to 0 because there's no acceleration in the y direction. All right, going up and down, there's no acceleration, the car is just staying flat on the road. Okay, so if we want to rearrange this real quickly, we can say that the normal force is equal to mg, so that our, going back to our equation up here, this is just going to be the frictional kinetic force is equal to mu k, which is our coefficient, times our normal force, which is mg. Okay. Now I want to take this and plug it back into our equation that we have in the x direction up here. All right, so if I solve this equation for the acceleration is just going to be minus fk over m. So this is just going to be mu k mg over m. Okay? And these m's are just going to cancel out, so you just have minus mu k times g. Alright, so the acceleration is minus mu k times g. Alright, well now that I have my acceleration, I need to find the initial speed, right? Because if we go back to our question, it says how fast was the car going when it became locked. So we're trying to find the initial speed. Alright, so the equation, if we look at our kinematic equations, we find something that has the information we have. We find this, which is the final velocity is equal to the initial velocity squared plus 2 times a times x minus x naught. Now, I want to take this equation and solve for initial velocity, but we can first do a quick simplification and say that the final velocity is 0, right? Because it's coming to a stop at the end. So we'll just assume that's 0. All right, so our initial velocity is then going to be equal to the square root of 2 mu k times gravity x minus x naught. So I just took this equation and rearranged it to solve for v naught. Now when I plug in all that I have, like the coefficient of kinetic friction, multiply that by gravity, and then multiply that by the distance, I get 58 meters a second. 58 meters a second is approximately 130 miles an hour, just for your reference. So there we have our answer for the final, or excuse me, the initial velocity. All right, moving on. So another example. In the figure, a block of mass m, which is 3 kilograms, slides along a floor while a force F of magnitude 12 newtons is applied to it at an upward angle theta. The coefficient of kinetic friction between the block and the floor is mu k is equal to 0.4. Now we can vary theta from 0 to 90 degrees. The block remains on the floor. Right, so there's not going to be any acceleration or movement in the y direction. We assume that the block just stays on the floor. So what theta gives the maximum value of the block's acceleration, which is in the x direction? So we're trying to maximize acceleration in the x direction. All right, so if you off to the right, you can see that we drew some of our Freebody diagrams. We see that the block is being pulled up and to the right at some angle theta by this applied force. And if you look in the y direction, the only forces acting are the force of gravity, the normal force, and then some component of this applied force, which is going to be Fy. Now, if you look at the triangle that we made here, this Fy is just going to be equal to, Fy is just going to be F sine theta, right? Because sine is opposite over hypotenuse. We want to find this part. We have the hypotenuse, so we get that. Okay, now if we look in the x direction, we see something similar. There's going to be some acceleration in the x direction, and we drew acceleration up off of the actual free body diagram itself to denote that the whole body is going to be accelerating. You have this portion of applied force to the right, and which is just going to, so Fx is just going to be F cosine, F cosine theta with the same triangle. And we have the frictional force acting to the left. All right, so because we need Fk of the frictional force, we must calculate the magnitude Fn of the normal force. So the figure shows a free body diagram, and I just discussed all of that. So we can write Newton's second law for those forces along the y-axis as this. So we have our normal force plus our F sine theta, because those are both going up, so we're going to add those together. And then we subtract mg. So we have, we took our normal force, we added it with the bit that's applied in the y direction, and then subtracted the force of gravity, which is mg. Set that equal to 0 because it's not accelerating up or down. All right, so rearranging this and solving for our normal force, we just get mg minus F sine theta. Now, calculating the acceleration, A. So in the figure, it's a Freebody diagram for the motion in the x-axis. The horizontal component Fx is the applied force rightward. All right, so writing Newton's second law of motion along the x-axis is going to give us, so if we have the summation of forces in the x direction, it's mass times acceleration, this is the subscript in the x direction. We have our applied force, which is to the right, so we'll call that positive, and then we'll subtract the frictional force, which is just mu k times our normal force, and that's equal to mass times acceleration in the x direction. Now I want to take this equation and solve for acceleration, because that's what we're trying to find. We're trying to find theta, but if we solve this for acceleration, we can do a derivative, and you'll see why in a second. All right, so rearranging and again solving for ax, we get acceleration is equal to the force minus mu k, and that's going to be gravity F for m sine theta. Okay, so basically we took our Fn, which is in this equation, and we plugged in this whole bit here. All right, and then we solved for this acceleration by dividing through by the mass. And we get this kind of ugly looking equation here. So how are we going to solve this? Well, we know that we're really trying to find the maximum theta. All right, and the max acceleration is going to be when you take the derivative of the acceleration and set that equal to 0. So when you take the derivative of something, set it equal to 0, that's going to give us our maximum. So if we take the derivative of acceleration with respect to theta, which means we're taking the derivative of theta this time. Okay, so we get, when we do that, we get, all right, so we'll look at this term by term. Let me use a different color here. All right, so this term, the derivative of this term, again, with respect to theta, all you need to worry about is cosine theta. So the derivative of cosine theta is negative sine theta. All right, so again, the derivative of cosine theta is equal to negative sine theta, d theta, but we'll just worry about that. So we'll just say negative sine theta. All right, so we get negative f over m sine theta, right? So f and m are constants. We don't need to worry about them. They just stay there. All right, so let's go ahead, use a different color for this next term. So this is going to be minus mu k times g. Well, there's no theta in this term, so this is just going to be 0. So this is going to be minus 0. All right, now let's look at the last term. We have this minus, also this minus, so that gives us a positive. We have we have mu k times f over m times sine theta. So again, mu k, f, and m are all constants. They're just going to stay there. The derivative of sine theta is just cosine theta. All right, so there's a negative when you go one way. There's not a negative when you go back the other way. All right, so we get a positive, again, because these two negative signs change into a positive. We get mu k f over m, and this is going to be cosine theta. All right, now this was all set. Oops. Let me switch back to red here. This was all set equal to 0. All right, because again, we're trying to find the maximum. So, well, we can simplify this actually pretty quickly. This first term is negative, and the second term is positive. So if I can just set them equal to each other, move one to the other side, so we have mu k f over m cosine theta is equal to f over m sine theta. And what you'll notice is that f over m cancels out. All right, so all we are really left with is tangent of theta is equal to mu k. All right, if I want to find theta, I just take the inverse tangent of both sides. So I have the inverse tangent of our coefficient of kinetic friction. Again, this k is a subscript. Okay. And again, our mu k is given to us as 0.4, so we just plug that in. Theta ends up equaling 21.8 degrees. So this is the angle that will give us the maximum acceleration. All right, well, that's it for this lecture. We'll finish up next time with a quick lecture on drag force and terminal speed. All right, we'll see you then.